So in this video, we're going to do a brief walkthrough about the derivation of the magnitude of the cross product formula, which says that the magnitude of the cross product is equal to the magnitude of the two vectors times the sine of the angle in between. So let's do a quick reminder on how we calculate the cross product. So let's say we have vector A with components x1, y1, z1, and vector B with components x2, y2, z2. Then the cross product can be calculated by taking the determinant of a matrix with the entries I, j, k, hat, which are the standard basis vectors, and then the elements of vector A and vector B. So that would be x1, y1, z1 from vector A, and x2, y2, z2 from vector B. So if you take the determinant of this will give you the cross product. And to save some time here, I'm just gonna compute it and just put the answer out on screen. So this would be your cross product, and remember the cross product of two vectors always gives you another vector. So that's your cross product. And what we're gonna do now, well, actually let's say equals vector A cross vector B. Now what we're gonna do is we're gonna take the magnitude of A cross B and square it. So remember that this is equal to the dot product of A cross B dotted with itself, dot A cross B. And this is just equal to all the elements, the sum of the squares of the elements of A cross B. So if we're going to square this, then add it to the square of this, and add that to the square of this. And the algebra is going to be, again, extremely messy, so I'll just put the answer on screen. But what we're basically doing is just squaring this, adding it to the square of this, added to the square of this, by essentially taking the dot product. So just to make it slightly easier to read, I've color-coded. So the square of this, the x component, would be this in green, square of the y component would be that in blue, and square of the z component would be that in yellow. And you add all of this together because the dot product is not a vector, it's a scalar. So now we have some common terms we can factor out. So we have a y1 squared here and a y1 squared here. We have a y2 squared term here and a y2 squared term here. And I'm just gonna use screen. We have a, well actually no, it won't work that way. You got a pair. So I'm gonna redo this in red. You gotta pair this x1 squared with this x1 squared. And then this last one, now you compare this z1 squared and this z1 squared. So this way, all the terms with squared are being used. If you do that, you can rewrite it as, I'm going to use white, so factor out of y1 squared. And you have z2 squared plus x2 squared plus the red, we factor out x1 squared. So we have z2 squared plus y2 squared. And now for this final part in green, we'll factor out z1 squared. We have y2 squared plus x2 squared. And now we need to add all these terms in the middle, which we can actually factor out a -2. So let's do that. So that's what it looks like with the -2 factored out. So now we're going to put this piece aside for now, but we're going to come back to it later. So let's put a star here. And remember that this is all equal to the magnitude of the cross product squared. So now let's work with the dot product. We know that the dot product, so A dot B, is equal to the magnitude of A times the magnitude of B times the cosine of the angle in between. So now let's actually square the dot product. So let's square. If we do that, we get this. So we square this piece, that's equal to the dot product squared. The dot product is equal to this piece right here. And now we square that. And now we can use the formula A plus B plus C squared is equal to A squared plus B squared plus C squared plus 2 times the sum of the double products. So AB plus BC plus AC. So let's use that to expand this out. This piece, so this is x component squared, y component squared, z component squared, plus twice the sum of the double products. Great. So now we're going to actually add this whole piece with this whole piece, which we found earlier. So the first piece up here, it's equal to the magnitude of the cross product squared. And we're going to add that to this part, the left-hand side here, which is the dot product squared. So square, square, cosine squared theta. And now this is where the interesting part comes in. We look at this piece right here, and we look at this piece right here. They look very similar. So notice we have x1, x2, y1, y2, or sorry, x1, x2, y1, y2. Over here, you actually also have x1, x2, y1, y2. You have y1, y2, z1, z2. You have y1, y2, z1, z2. You have x1, x2, z1, z2. x1, x2, z1, z2. So actually, these match exactly. And if we add this -2 to this +2, these terms actually cancel out. So that works really nicely where we can just cross this out. Now, all we need to add now is this initial part to this initial part. So let's do that. So this is what it looks like now. Now you can actually combine these terms. You'll notice this has a y1 squared, y1 squared, x1 squared, x1 squared, z1 squared, z1 squared. You can actually combine this into one large expression. So once you combine this, you get this large expression, and now you'll notice these, this, and this. They're all the same thing, so we can, again, factor it even more. So now we have this product. And now this is actually very interesting because this looks just like a magnitude, but without the square root. So this is actually just the magnitude of our vector b squared. Remember that b is defined as x2, y2, z2. And this part, this looks like a magnitude without the square root, and it's just the magnitude of a squared. Because vector a is defined as x1, y1, z1. So now let's bring our left-hand side back down. So we have the magnitude of the cross squared plus a squared, b squared, cosine squared theta is equal to this. Now let's subtract this term on both sides, magnitude of a squared, b squared, cosine squared, and we end up with a cross b magnitude squared is equal to magnitude of vector a squared times magnitude of b squared minus this. Great. And now we see we can actually factor again these common terms. So now we can say and this part, this is actually sine squared theta by the Pythagorean identity. So now we have the magnitude of cross product squared is equal to this all squared. And now we can just take the square root on both sides. And that gives us our final solution, which is that the magnitude of the cross product of two vectors is equal to the product of their respective magnitudes times the sine of the angle in between. So that is our magnitude of the cross product formula.